Hey there, math fans. This is going to be a video about the slide in my series where I go through a project from my playground math I made for my honors calculus students many years ago. I just finished making the video. The first 9 to 10 minutes is more of a derivation. That took much longer than I thought. So I just wanted to warn you about that. So if the derivation's too much, or I'll get better at making these videos, but you could skip past the first 10 minutes and then you can just see me discuss the problem. I make some animations. That might interest you more if the math isn't as interesting at the beginning. But I did give some derivations for the first about 10 minutes. Then from there on out, I talk about the project. And then at about 12 minutes, I show a bunch of visuals, which might be interesting. So I just wanted to give you that warning. All right. Hello, math fans. This is the first question in my math playground. Please watch part 1 for an intro. This is about someone going down the slide. So we're going to talk about this particular thing. Again, this comes from a project I used to have my honors calculus students do about 13 years ago. This particular problem, as I mentioned in the previous one, has a lot of meat to it. We're not going to spend as much time as we could. In fact, as I was preparing the video, I realized that my project had a few things that were inaccurate. So I've since fixed it, and the posted project is correct. But ultimately, someone who knows some physics knows there's a short answer to this question. But the goal of my project was to practice parametric equations. And so I gave the students this parametric equation. And as I thought about it, again, this is many years ago I made this, and I've learned a lot since then. There's a much cleaner way. A physics person would know how long, and ultimately the question I ask is, you have these two people, and they want to get to the bottom of their respective slides at the same time. This person has an initial velocity of 0. This person is going to have to go faster because they have further to go. And the question asked, how fast do they have to push off to get started? And this was 10 meters and this was 5 meters. That was the question I wanted them to ask, but I phrased it in a way where they had to use this equation. So I will in a moment talk about the kind of the physics approach. Really, it's not even a physics approach. It's just a direct line approach. But I wanted my students to get to experience parametric equations in X and Y, where this is X and this is Y, which is not a very clean way to do the problem. So I want to admit that up front. I'm just going to say a few words about this. This is more for students that are taking Calculus 3. But ultimately, if you're going to take a course in something sliding down an inclined plane where there's no friction, you're going to have to study things like the force due to gravity, Fg. These are going to involve vectors, the normal force, and I am not claiming in any way to be an expert on this, and then the force and the direction of the incline. Now, as I was reading up for this question, what most people do is they just call the incline the x-axis, which makes some things easier. I think there is one advantage to what I'm doing here, which is that I can animate this. And I will show you an animation of this in a second. And if I hadn't done this, yes, I would have answered this particular question, but I gain a little bit more information from the animation. So in a moment, we'll have these two people go on the slide, and I couldn't have made that as easily as I did if I hadn't gotten these equations. So very briefly, what I did was I cheated my way through the physics a little bit, and I said, well, no other force really matters here since there's no friction. There's just gravity, but I need the gravity to be projected into this direction. And there's a way to do that. This is called the projection vector, and if you take Calculus 3, you do that. So this is the projection of this vector, and I've removed all masses. So again, a physics person would be mad at me because the force actually has mass in it. I just basically figured out how much acceleration was in the direction of my incline. So that's not the way you would do that in physics. You would draw a force diagram, account for everything, and that is better because that's easier to adapt to adding friction and other things. So I'm doing I'm not teaching you very well here, but I want to quickly get to this. So the projection onto 1m, why am I using 1m? So the slope of this line is m. It's going to be a negative number. B is going to be the y-intercept. If you want a vector that has, let's say, slope -2, there are lots of vectors that do that. You need the change in the rise over the run, the change in y over the change in x to be -2. And there's often a trick we do. We just pick one that works, and the one that works is putting a -2 here and a 1 here. Okay, so that's why I'm projecting onto 1m. This is the projection. It's a nice little, it comes about from learning the dot product. So those of you taking Math 126, you'll know how to do that after section 12.3, which is the third lecture of that discussion, how to do these projections. So maybe this gives you some reason to learn that. But this gives you the acceleration in the x direction and the acceleration in the y direction as the x and y are given here. And then we can do normal integration stuff. Integrate with respect to, this is a number. I know it's a lot of stuff you're taking in, but we'll do something with this at the end. And I gave the students all this. This was a Calculus 1 course, and they were already given all these formulas, so they didn't have to know where it came from. But I thought if I made a video, I wanted to explain how I got them. So integrated my initial velocity. That's a different challenge. I told in the problem, it says this is the initial speed, which means the velocity in the x direction squared plus velocity in the y direction. So again, this is, I realized as I was doing this, I was like, oh, I did a lot of stuff to set this up. And there was even an error in my setup, I realized, that changed the numbers slightly. So please don't trust me. Do these calculations on your own. But I said, so this is turning this into a vector, the velocity in the x and y direction. It turns out that forms a little triangle, with this being the length of that vector. So that's the initial velocity. This is the initial x velocity, the initial y velocity. Because of the slope, the ratio of these has to be m, and so you can solve and you get these equations for the initial x velocity, the initial y velocity. It's very unnatural to do this in terms of slope. Usually people do these in terms of the angle, and so you get formulas involving sine and cosine. So again, this was not a clean way to do it, but I was sort of, I think at the time, I don't know if I agree with myself, but I was thinking, what do my students know? And I was trying to remove any trig or anything else and just say, you give me the slope, here's the formula. And then the initial y value was, so anyways, I gave the students this, and then I asked them to do a few things. Verify that every point on this curve is on this line by just plugging in, verify that the derivatives match up, and then I asked them some questions using that. And so before I get to that question and show you, and I'll talk briefly at the end. If we were in class, I would say remind me, but you can't do that, about the Bristochrone problem. Which is also about how you would design a slide. But right now we're just doing straight slides. Okay, so then I went and thought about it, and I'm like, you know what? If you just want to make this a one variable calculus problem, there's an easier way. I know this is pretty dense. I'm trying to get through it quickly here. But really the goal is just to introduce you. So if I pretended this was the x-axis, the problem becomes easier because it becomes a one variable problem. And you can just figure out the acceleration in that direction, which is this. And now I am using angles. I'm using the physics approach. And then you can just make everything positive. You just think of that as the positive x-axis. And then you can integrate, and this is now representing the velocity in that direction. And then you get to compute the distance in that direction. And if L is the length from here to here, you can just figure out when you travel that distance. And this ultimately is a quadratic. So what I did was I subtracted this from both sides, and I used the quadratic formula, and that's where that came from. I know that's, again, a lot to take in. I then checked this, because back when I did this, I wasn't as keen on checking as I am now. I checked this against several online physics calculators about the time it's going to take, and I was getting the same answers. But that took some work to sort of clean up what I had. Okay, anyways, so what I gave the students was this. I said, assume I've already given you the formulas. You don't have to derive them. It's all given in terms of m and b. And notice I was trying to avoid the angle and everything. And I said, okay, you've got these two friends. They want to reach the bottom of the slides at the same time. Well, really, probably the second friend wants to get there at the same time. He's really going to have to push off. So this one starts from rest. So they're going very slow, and they just let the gravity take them down. This one starts much higher, and they're inclines, so they're going to have to push off pretty darn hard if they want to get there at the same time. So ultimately, you could use this formula. You could calculate the time for the one where you know everything, and then plug in the numbers for the one where you only know some of the stuff, and then set them equal and solve. But I had students actually fill in these formulas. So I'm going to zoom out a little bit. Okay, so I had them fill this in. And this is a parametric equation. It says here's the x component, here's the y component. Very useful if you're trying to animate the motion or something else. I had them figure out the slopes. Now, in order to figure out the slopes, they did have to do some trig, or had to solve for the sides. But there's an easy way to do that. Tangent of 30 degrees is going to tell you what this side divided by this side is, which is the slope, except that it's going to give you a positive number. So you have to, there's always this issue about whether you make it positive or negative based off of the situation, because it would be the same ratio if the triangle had drawn this way, but it would be positive slope. Anyways, and then same thing for this one, the slope is going to be, and in my work in a second, I'm going to use an n for that one, in the animation I'm going to do. And those are the two slopes, and the equation for this line is going to be this mx plus 5, and the equation for this line is going to be this nx plus 10. But these equations, notice, don't involve time at all. They're just the slides themselves. Sometimes I think of this as the path. Students get confused about this in Calculus 3 when they're working with parametric equations, because you can have an equation that describes the path, but that doesn't tell you where someone is. There's an infinite number of ways you can get on the slide. You can go faster, you can climb up it, right? So if you want to actually incorporate time, there are so many different what we call parameterizations. For example, if you just had x be t and y be mt plus 5, that's a parameterization. It works in here, meaning if I call this t. But it's not going to be accurate in any way in terms of gravity. That's when the challenge comes in. It's when you want to have motion that actually meets other criteria. And motion under gravity is often hard to analyze, the more complicated the shape is. We can do this because we were able to project it onto a straight line, but it still came out to be pretty messy. So I filled in all of these numbers with the appropriate slopes and the appropriate initial values. And there was only one number I didn't know, which was the initial velocity for the second person. I plugged those in, and here's what I got. So let's show you the animation. So here we go. So here's the first person. I drew them on the same axes. Here's their slide. Let's get rid of the second person for a second. There's the two lines. If you can see it, there's a 10 right there. There's a 5 right here. Those are the two slides. I made the blue slide have an angle of 25. The red side has an angle of 30. If I animate this is the actual equations of this person going. That first person on their slide. They're going down here. Sorry, I couldn't get it to draw any better. And they get to the bottom at 2.02 seconds. And that ultimately is solving a quadratic. You're going to find when the y is 0. So I plugged in all the numbers, found when this was 0, quadratic formula. I got a negative and a positive root. The positive is the only one that makes sense in the situation because we're starting at 0. And I got that it was about 2.02 seconds. I'm at the bottom. And that matches up with all physics formulas. There's shortcut formulas for that. But if I hadn't done this, I wouldn't have been able to make this nice animation. So it starts off really slowly, picks up a little bit of speed. This is not real time because that's 2 seconds. So I've slowed it down smaller than regular time. If I made it regular time, it would be fast. So there we go. There's the person going down the slide. 2 seconds, they hit the bottom. So our job was then to have this other person get there. But now if the other person is just going to go down the slide, and they start at the top, and they don't have any initial velocity, let's look at that. Oh, they're not even going to be close. So this person will, when this gets to the end, they're only going to be right there. So they had needed to start a little bit faster. And we solved that. So I solved that. I actually just put it into a solver. I was a little lazy here. And I got 7.52 meters per second. And you can solve it with the quadratic as well. So let's go a little faster and see what happens. So we know it has to be 7. Let's say they start off at 5 meters per second. That's a pretty darn hard push. This is not that realistic. They get going pretty fast, but they don't quite make it. They don't make it to the bottom at the same time. They need to be going 7.52 in order to make it there at the bottom. 7.52. Let's put it in exact. And then let's go from the beginning. So they had to push off really hard or get a shove, and they make it there at the bottom. So I always thought that was an opportunity to work with parametric equations, because notice there's all sorts of ways I could have parameterized that. I can make it slower, I can make it faster. And so this idea of taking a path and parameterizing it is a big idea. And if you're going into Calculus 3, it's something you have to get used to, because motion or curves in 3D are pretty much always parameterized. So there you go. Hope that's interesting. I try to make it so I could play around with this. Okay, so before I finish, I was going to just mention there's a bigger question about what if you wanted to get from point A to point B as fast as possible. And there are plenty of other videos about this. You can search online for baristochrome problem. But it turns out if you have a little bit of a sloped slide, that's going to be better, because you get going faster initially, which makes sense. But this was a problem that was not easily solved. It was solved in the time of Isaac Newton. So I'm going to say a little bit about that. I'm not going to derive it because it's a big derivation. Okay, let's stop this. Slowing my computer down. So here's the question. Some of my students have seen this curve before. It's an example of a cycloid. So that comes up in our Calculus 2 course, and I believe in our Calculus 1 course. They have some examples of this on Wikipedia. One that's interesting is this one. I don't know if I can make. Can I make this bigger? Oh, there we go. If you compare the yellow here with the black gets there much faster. So if you're trying to get from point A to point B under gravity, if you're trying to walk there, a straight line's the fastest path. But if you're saying what's going to happen due to gravity, you want some sort of slope. It turns out to be this unusual shape, this cycloid or baristochrome, and it turns out this pops up in various places. It's not a parabola, it's not a circle. Okay. So there's a long history of this problem and it being posed, people playing around with it, figuring out how much time for different shapes. And those setups would be similar to what we're talking about. But the first proof is attributed to Bernoulli. Now, the Bernoulli family is a very interesting history. I just wanted to pull this up. That they had the father here had 4 kids. 2 became these outstanding mathematicians, and then many of their children were. So it's it's the most prolific mathematical family, I believe, of all time. I wanted to note that he is noted with this particular Bernoulli is noted with being one of the first teachers of Leonhard Euler, who I talked about in a different video. I think it's supposed to be Leonhard Euler, but I'm giving the pronunciation, the American pronunciation. Okay, but a contemporary of Newton. There was a mention of that Isaac Newton also solved this problem separately, but didn't publish it under his own name. And Johann recognized, based off of the writing, who did it. He said, I can recognize a lion by his claws or something. So some interesting history around this problem. I think there are plenty of videos about that, but that's not for me to make. Check those out. So a lot of real important, significant old questions relating to the slide. This was hard enough just to go down a straight slide. When you start to account for gravity, things get, a little bit spicier. There's more going on. I hope you found that interesting. In the following videos, I'll do merry-go-rounds and swings and seesaws. Those will be a little more tame mathematically, but I think I'll be able to generate some nice visuals. Hope you found that interesting.